In this lecture, we'll be discussing type 1 errors, type 2 errors, and the Bonferroni correction. Now, I imagine that it's probably a statistical course which led you to this content, and that is because you'll rarely encounter any of these topics outside of the classroom or within the field. That being said, you might sometimes hear the term type 1 error tossed about, so I would be negligent in my responsibilities as an educator and content creator if I didn't, at the very least, present the term to you in a generalized manner. So as far as Bonferroni is concerned, in all likelihood, you will never ever utilize this concept. You only encounter its existence if you have a particularly difficult individual on your thesis committee. If you run an ANOVA with post hoc analysis, which is appropriate in almost every instance as compared to multiple t-tests, the entire case for Bonferroni correction vanishes and the entire concept with it. We'll begin with discussion of type 1 and type 2 errors, after which I'll cover Bonferroni. Don't feel obligated to watch until the end, and remember to please like and subscribe. What is a statistical error? There are two types of statistical errors: mistakenly rejecting a true null hypothesis, a type 1 error, and mistakenly failing to reject a false null hypothesis, a type 2 error. And again, you'll more typically encounter type 1 error, at least as far as the terminology being discussed. So a type 1 error is when the P was low and we did reject the null hypothesis, but it turns out the null did not have to go. So we assumed that the status quo assumption was incorrect. However, it actually was. So here's an example. We thought that there were no peanuts in our caramel corn, peanuts being advertised on the bag. However, upon further research, the peanuts were all at the bottom of the bag. So again, we performed our methodology of analysis. We came up with a low p-value, lower than our alpha value. So let's say our alpha value was 0.05 and our p-value was, I don't know, 0.0001. Therefore, we rejected the null hypothesis. However, it turned out that we mistakenly rejected the null hypothesis. The null hypothesis assumption was actually correct, and we accidentally rejected it. A type 2 error is the P was not low, and we did not reject the null hypothesis, but it turns out that the null hypothesis should have been rejected. So in this case, we assumed that the status quo assumption was correct. However, it actually was not. So here's an example. We believed that there were raisins in our ice cream as promised by the store clerk. However, upon further review, the raisins were actually chocolate chips. So in this case, we were applying methodology. We had a P that was higher than our alpha value. So we'll say our assumed alpha was, again, 0.05, and our P was, I don't know, 0.15. All right, so our P is 0.15, our assumed alpha is 0.05. So as a result, we did not reject the null hypothesis, but it turns out that we actually should have rejected the null hypothesis. The family-wise error rate, also known as also known as FWER, F for family, W for wise, E for error, R for rate. The family-wise error rate is the probability of rejecting a true null hypothesis, a type 1 error. Because remember, if we mistakenly reject a null hypothesis, we're committing a type 1 error. So what is the probability of a type 1 error rate or a type 1 error occurring? Well, to determine this, we have to calculate the family-wise error rate, and that is 1 times 1 minus alpha to the power of m, m being the number of tests. So let's take a look at that. If we're only performing one test, so we're only performing, let's say, a two-sample t-test. We have category A and category B. All right, our alpha is 0.05. Therefore, our type 1 error for the experiment is 5%. 1 minus 1 minus 0.05 to the power of 1, 1 being the number of tests, that provides us with the family-wise error rate. Again, this is our alpha value here. This value 1 is static regardless as to anything else in the equation. We're performing one test. All right. This value, this 1 as well, is also static regardless. So the only values that we're going to be changing as it depends on the circumstances are this value here and this value here. This will be our alpha value, and this will be the number of tests. Make sure you don't get confused with order of operations, okay? So it's 1 minus, parentheses, 1 minus the alpha value to the power of the number of tests. So if it's only one test and our alpha value is 0.05, then our family-wise error rate is 5%. That is the percent potential of committing a type 1 error. And it makes sense, really. Our alpha value is 0.05. Our type 1 error rate is 5%. Now, if we're performing 5 tests, our alpha value being 0.05, then our type 1 error rate for the experiment is 22.62. What changed? Well, as I mentioned previously, 1 is going to remain the same, both outside the parentheses and within the parentheses. Our alpha value is still 0.05, so we place that there. However, we're running 5 tests. So there, our m exponent is the number 5. So 1 minus, parentheses, 1 minus 0.05 to the power of 5, that comes out to 1 minus 0.7738, which provides us with a family-wise error rate of 0.2262. We need to move the decimal place over 2 spots to the right, and we end up with 22.62%. So in this case, if we're performing 5 tests, the percent chance that we commit a type 1 error is 22.62%. And how this works out is like this. And we're going to wrap up type 1 error rate, family-wise error rate. Then we're going to talk about Bonferroni. So after this slide, if you want to head out, that's okay. Like and subscribe. I'll see you the next lecture in the playlist. So let's say that we have samples. So we have samples here. These are different observations, 1, 2, 3, 4, 5, 6, 7, whatever. And each one of these is a category. So we have a bunch of numerical observations here, a bunch of numerical observations here, a bunch of numerical observations here, and here as well. And we want to compare each category to the other. So we want to compare category A to category B. We want to compare category A to category C, and we want to compare category A to category D. Well, we could either run 1, 2, 3 two-sample t-tests, A to B, A to C, or A to D, or we could just run an ANOVA. And we would run the ANOVA if we were interested in comparing A to B, A to C, A to D, B to C, B to D, C to D. That's what we would apply an ANOVA to do. And we'll get into ANOVAs in a few lectures or so in the playlist. However, if you're in a situation where you want to compare A to B, A to C, and A to D, that's 3 separate tests, which would mean if we were doing the family-wise error rate, that would be 1 minus 1. If we had a alpha value of 0.05, it'd be 1 minus 1 minus 0.05, and then our m exponent would be 3. And that would then provide us with the probability of committing a type 1 error. However, if we wanted to just be like everyone else and do an ANOVA, and to avoid that problem from occurring, we could do such, and then we wouldn't really need to be concerned about family-wise error rate. Our family-wise error rate would be 0.05. However, if we were stuck in our ways and we wanted to do, instead of an ANOVA, A to B, A to C, A to D, we could, to try to reduce the probability of committing a type 1 error, utilize the Bonferroni correction. And that is Bonferroni over there to the right. So in statistics, the Bonferroni correction is a method to counteract the problem of multiple comparisons. And how you calculate the Bonferroni correction is rather quite easy, at least compared to the family-wise error rate. And all it is it's the original alpha. So we were working with an alpha value of 0.05. We would divide that alpha value by k being the number of tests. So if we wanted to run 3 two-sample t-tests, A to B, A to C, and A to D, we would just divide our alpha value 0.05 by the number of tests, in which case that would be 3, and that would provide us with the Bonferroni correction. Now, in this case, in this example slide, we're running 5 tests, and we're using an alpha value of 0.05. If that were the case, our Bonferroni correction would be 0.05, our alpha value, divided by the number of tests, 5, and that is 0.01. So what does this mean? What do we do with the Bonferroni correction figure? Well, you would mention that you were utilizing the Bonferroni correction in your methods section if you were writing for publication, and you would mention which tests you're running, how many tests there are, and what the Bonferroni correction figure is then. So you would say, we applied a two-sample t-test comparing A to B, A to C, and A to D. And as a result of such, we calculated the Bonferroni correction as being the Bonferroni correction figure, which we then utilized to test, or we then utilized the Bonferroni correction figure as a figure in which we utilized to test the hypothesis for each of our outcomes. And what this would mean would be, instead of using an alpha value of your original alpha, 0.05, you would instead only find results to be significant based on this figure here. So if you were running 5 tests and your original alpha value was 0.05, and you wanted to do 1-to-1, one to the other, and so on and so forth, instead of using the alpha of 0.05, you would then use the alpha of 0.01. The Bonferroni correction of 0.01 would replace the alpha, and only p-values which are less than 0.01 for those particular 5 tests that you're running, which are interrelated, only p-values which are less than 0.01 would be found to be significant. And that is how the Bonferroni correction is utilized. Again, you typically won't see this being utilized, and it won't be suggested as far as its utilization is concerned, unless you are working on your thesis and a member of your thesis committee suggests it, in which case you would respond with, well, why don't I just run an ANOVA? And then you could avoid all this. But if you do find yourself forced into a situation where you have to use Bonferroni correction, you'll now know how to calculate it. So a couple of things to remember if you made it to the end. A type 1 error is the probability of falsely rejecting the null hypothesis if the null hypothesis is true. A type 2 error is the probability of failing to reject the null hypothesis if the null hypothesis is false. If you are utilizing a Bonferroni correction, be sure to state this within the methods section of your research. So that is all. Best of luck in your course. Best of luck with your research. Hope to see you in the next video in the playlist. Take care.